So what page is the equilibrium review sheet on? 245. So those of you playing at home, this is on page 245. So here we go. Okay, so we have a couple of questions here about equilibrium, which is a unit we've been discussing now for a couple days. First one is, why does increasing the temperature cause a reaction to speed up? What say you? Why does increasing a temperature... It's about... Yeah, we got a lot of good... We got molecules are moving faster. Molecules moving faster. Ergo, more colliding. And we need these molecules to collide. And if they collide with enough energy, they're going to react, right? And the more collisions, the more likely you have a reaction. Well, if the temperature is increased, then they're moving around faster. Temperature is proportional to kinetic energy. So, there we go. Increasing temperature moves around faster. And then we also learned that ergo means therefore. Number 2, why don't all collisions produce products? The first thing is they have to have enough. Yeah, they got to have enough energy. They need to have more energy. Trying to write activation energy also in there. Oh, that's horrible handwriting. That pen. It's totally the Promethean pen's fault. It's not me. Activation. All right. And then what did you say back there in the back? Orientation. The way they are facing when they collide makes a huge difference. Huge difference. They have to be facing the right way when they collide. Otherwise, they'll just bounce off of each other. So if you're doing a reaction between A and B to produce AC, and then B is by itself, when they collide, you need A to collide with C. If A collides with B, you're not going to have a reaction. You need to have the proper pieces hitting each other. That's what orientation is a reference to. Okay, number 3. Is the statement, at equilibrium, the concentration of the reactants equal the concentration of the products? True or false? It is false. You are correct. How could we correct that statement? It's not the concentrations that are equal, it's the rates, the speeds. In last class, I think I was throwing markers at someone, and we tried to get to the same rate of exchange, right? It was throwing markers back and forth, and we got to a 1-to-1 ratio where I threw one and he threw one back at me, and it was in balance. Did we have the same amount of markers in our possession? No. He had 3 markers and I had 1 marker, and we threw one at each other, and then he had 3 markers and I had 1 marker, and we threw one at each other, and the rate of markers flying through the air was 1 for 1. And that's really what we're talking about equilibrium. Kind of like these adorable little ants down here. Look how cute these are. Do they have equal piles of whatever the heck that is? No. And they're exchanging rocks. Watch as they both pick up little rocks, or maybe they're rice, or I don't know, maybe they're caviar. And they both steal. Is the size of the pile going to change? No, because the reaction rate, the exchange rate is identical, so the size of the pile doesn't change. That's what occurs at equilibrium. The quantities stay constant for a while. So it took me a long time to draw that so that would work. I didn't draw that. All right, what is the equilibrium constant expression? The expression is the setup. So K equals the products on top and the reactants on the bottom, right? So in this case, K would equal H2O squared times Cl2 squared. Where are the 2's coming from? The exponents. The leading coefficient. Yep. That guy in the back of the room knows all the answers today. And then That's the fourth, so HCl is to the fourth. And then O2, its coefficient is a 1, so if you want to put a 1 down, you can, but it doesn't have any impact, does it? Hey, last class we did almost the same question, but the water disappeared because it was a liquid, right? This time it's a gas, so it's staying in there. That's a reference to what I said in the notes in last class. Anytime you have a solid or a liquid, solids and liquids get replaced with the number 1 in these expressions, which makes number 5 really easy to write the answer to. How many of them are solids in number 5? 2. That's a solid, and that's a solid. So this one is equal to K times 1 times H2O over 1. Right? Because 2 of them are solids. Anytime we have a solid or a liquid, we replace them with the number 1. Do I actually have to write the number 1 in there? I'm just doing it so that I know I thought about it. So that I know that I thought about it. And then you guys also can see that I thought about it. So we have the products on top. Replace that one with the number 1. H2O is a gas, so it's in there. That's a solid, so on the bottom. And we have our equilibrium expression. Okay. Si, senor. Well, the gas, we haven't been told the value for a gas, but whatever value they tell us for the gas would pretty much be the value for K, wouldn't it? Because K equals the gas. So if the gas was 2, then K is 2. So. All right. Wait, didn't we just do number 5? There we go. Edit achieved. Number 6. If the concentration of nitrogen is decreased. So this is one of the Le Chatelier questions. And Le Chatelier, he was all focused on how reactions re-achieve balance. And I often kind of turned these into little seesaws, right? And so right now the reaction's in balance. The ants are exchanging rice grains at an even amount. Or the markers are flying through in an even amount. But if someone messes with the balance, the reaction's no longer going to work the same. So in this case, the nitrogen is decreased. That would be the equivalent of something coming along and removing the nitrogen. Is it still in balance with the nitrogen gone? No. This is, in order for this reaction to occur on this product side, it's got to be water plus the missing stuff. It can't hit the missing stuff if it's missing, can it? So it can no longer go to the left because it doesn't have the nitrogen. Can it still go to the right? Yeah, these two things can still combine and make products and bring it back into balance. It would take a while to get back to balance, but when you remove something, the reaction shifts to replace it. So let's reverse that. What if someone added a thing? What if this question had said, nitrogen is added? That's not going to work. Nitrogen is added. Is it in balance if there's way too much nitrogen? No. So then it would shift to get rid of that extra also, wouldn't it? So reactions can go both ways. And the idea with these Le Chatelier questions is we're in balance, and then this change occurs. All right. Number 7. Will an increase in pressure cause a reaction shift to the left or the right? Also, no change is also possible. Well, I typically have trouble visualizing changes in pressure. Pressure is the amount of collisions per second. But I just have trouble visualizing that, so I often convert these to volume. What would be happening to the volume if we have an increase in pressure? Volume would be decreasing. And the reason I changed that is it's a lot easier to visualize how the reaction shifts if the space is smaller versus bigger. So what we're supposed to do, if we're talking about volume or pressure, is count the moles of gas. Intentional pause. Count the moles of gas. How many moles of gas are on this side? only 1 mole of gas. That is a liquid, right? How many moles of gas are on the product side? 0. So I'm comparing the moles of gas. Which one takes up less space? 1 or 0? 0. And so I've said less space because the volume is decreasing. So this reaction is going to shift to the smaller side that takes up less space. All right? So that's the logic there. Now, let's go back to the pressure side, because this one, since there's all these solids and liquids, isn't actually too hard to think about pressure. So, is the solid impacted by the pressure? Does the solid get bigger or smaller when there's more pressure on it? No, it's not impacted at all, is it? The liquid's the same way. If you put pressure on a liquid, it doesn't really contract or expand or anything. It's just like, I'm a liquid. But the gas, if you put pressure on it, it will compact, won't it? And so these gas particles will hit those liquid particles more often. What happens if they hit more often? More likely to have a reaction, yeah. And so we have more reactions between the gas and the liquid, which is why the reaction shifts to the right, because there's more reactions, there's more pressure, more collisions. Alrighty, number 8. Look at all this space I have to write in a horrible handwriting. First, let's write the expression. Always a good idea to express yourself, whether it's through political signs or the clothes you choose. What am I talking about? I'm just filling the air while I write. All right. Products over reactants cubed. So I got my expression, my horribly handwritten expression. On the test, you will be asked to do the expression a couple times. Don't flub this. Just set it up. That's just the setup. We're done. If this question said, what's the expression? That's it. And then the next part is, now solve for something. So we plug in values. Going to use the math symbol. So now we plug in values. I don't know if you know the 3 circles. Have you seen the 3 circles before? So the idea is like you've just done this setup and now you're going to plug numbers in, and that just communicates to people that, you know, we're doing something. We're plugging something into that. I don't know what the 3 circles are called, but I've seen them enough times. CO is 0.304. One of the key things in this plugging in is, man, you really got to make sure you plug them in the right spot. It can be embarrassing if you plug them in the wrong spot. How'd I do? Did I plug everything in the right spot? Did I use the expression correctly? I've missed one thing. What did I miss? Yes. And I missed it because so many of you all will forget this one little cube on the test, right? If you don't cube a number, that's real different, right? Like if your paycheck was supposed to be cubed and you made $5, what's 5 cubed? 125. There's a big difference between cubing it and not cubing it. Like here's your $5 versus here's your 125 bucks. You would care, wouldn't you? So there's a big difference between 0.3 and 0.3 cubed. Make sure you cube it. Also, I think I suggested using the flying seagulls to kind of help yourself out in your calculator. Or plenty of people will just work out the top, write it down, work out the bottom, write it down, and then do the top divided by the bottom. I don't have a calculator in my head, so I cheated and I typed the answer ahead of time. K equals 0.980. That is the equilibrium constant for K. Yes, sir. So I wouldn't round the math you're doing here. So if you do this math, I would write down I'd write down like 6 values, a whole lot of values. And if I was doing this math, I'd write down a bunch of values. And then I would type this number in carefully, and then type that number in carefully into my calculator. if you're good with a calculator, maybe you know that you press second enter, and it'll bring up the last thing you typed in. I don't know if you know that. So if you type this number in and then go divided by second enter, it'll whatever the last thing you typed in will magically appear there, and that saves you that error of typing. Because I'm really dyslexic as a calculator typer, which doesn't do good things for your math, does it? If you type in numbers in the wrong order, your calculator doesn't know what you mean. All right. Name 5 ways to speed up a reaction. Now, I'm going to take you back to a time we watched a video about ways to get a date to the dance. Do you remember that? Wait, you know what? I'm not going to record this part. Some of the best dating advice I've never given. So, the 5 ways in terms of a reaction is you need more moles. If you add more to the reaction vessel, they're going to collide more often. Step 2, smaller volume. Smaller volume. Well, moles and volume are interrelated in what term? What is that term that has moles and volume together? Molarity, right. So this is actually a reference to molarity, because molarity is N over V. So if you increase the moles, you've got more molarity. If you decrease the volume, you've got a greater molarity. Those are both molarity references. Temperature. If you increase the temperature, we're going to get more collisions, right? They're going to hit more often, more often. The 4th one only applies to solids. Break up solids. So maybe you go from chunk to powder. Chunk is a gross word? Oh, I like chunky peanut butter. It's delicious. Oh, yeah. Chunky peanut butter is the best peanut butter. If you don't like it, you're wrong. So, like aluminum, the metal aluminum is ridiculously reactive as a powder. As a solid, as pipes, it is also very reactive. But the second it's made, the surface reacts. The surface of aluminum pipes is actually aluminum oxide. It's got a thin oxygen coat. If you cut through aluminum, the exposed aluminum immediately reacts. The only way you can see it is if you have it under argon gas. Then you can see what it looks like unreactive. And number 5 was catalyst. And we did a lab last class, for those of you who were here and didn't skip school, where we did a reaction, then we did a reaction with a catalyst, then we did a reaction with an even better catalyst. And we got to really see how catalysts can speed up a reaction. The first reaction, it was decomposition of hydrogen peroxide. We put the hydrogen peroxide in a beaker, and it barely bubbled at all. You probably didn't even notice the bubbles. Then we had a catalyst, and it started to bubble pretty quickly. What happened with the third beaker and the stronger catalyst? Yeah, and it like bubbled over and boiled, and there was steam in the air. Remember the steam shooting up in the air? And it was like, yeah, it boiled because it was so fast and so hot. Number 11. Where's number 10? What? Is there no number 10? Oh, that's right, because that was one of the questions on the test, so we deleted it. Why does an increase in concentration cause a reaction to speed up? All about the collisions, right? If you have more reactants, you're going to have more collisions. So increase in the concentration increases the collisions. You don't have a diagram. Did you draw a diagram? Did you try? Let's do one exothermic and one that's endothermic. The x-axis is the progress or time axis. You could call it either way. You could say it's the time factor or it's the progress, how things are progressing. And then the y-axis is the quantity of energy. Energy. Okay, so if it's exothermic, and we start here, where should we end up? Lower or higher? It's exothermic. Lower. It's giving off energy. So the reactants versus the products, the reactants start, bless you, just no more sneezing, okay? Thanks. The reactants start higher than the products, but then in between them, we have that boop, 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 right? I think I just said boo-boo, but anyway. We have that hill. Versus the endothermic, if the reactants start here, the products finish higher. Still has that hill. Boop, 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 boop. There we go. Great sound effects. Great sound effects. Both of them have the hill. What do we call the hill? Activation energy. And the common symbol for that is E sub A. E stands for energy. A stands for activation. It's activation energy, or energy of activation. So we got most of the pieces. What does the question say? What pieces are we supposed to include? Ooh, are we supposed to have a catalyst on there? So where would the catalyst go? Below it, hopefully, right? Hey! Woohoo! So the catalyst should reduce the amount of energy that you have to go up. So go boop, 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 versus boop, 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 boop. All the sound effects really improve it. This catalyst here, wow, that's kind of representative of the manganese oxide we put in the hydrogen peroxide last class. Is the second we put that black stuff in there, all the energy was given off, right? It was really fast, very reactive and intense. Was this a class I tried to pick up the beaker afterwards? No, you would remember because I did a little hee! Because I went to pick up the beaker and I didn't think about the fact that this had just boiled. And it was super duper hot because the catalyst decomposed the hydrogen peroxide and all of it boiled and shot up and we had steam and everything, right? It was all over the table back there. And the beaker was super hot. And like right afterwards, I was like, so what is this? And I picked up the beaker. I was like, oh my God. So stupid. So anyway. Yeah, I just recorded all that. That's fantastic. You're welcome. All right, number 13. I wish I had more space. Let me pause and adjust my screen. Space achieved. Okay, so let's write the expression. What's the expression for this reaction? Products over reactants, yeah. The products are, does anybody remember the name of this product that I'm writing right now? That I just wrote? Acetates. Acetate. I had a couple of ideas out there. And then the other one, I'm writing it wrong, but it's the same number of hydrogens. This has all 4 hydrogens grouped together. I just moved the one to the front. That's acetic acid. So what we're supposed to do is plug in the values from each trial or each experiment and see what value we get. So if I plug in the values for the first experiment, which I'm doing right now, I'm going to get a value for K. And that's the value for K, 1.8 times 10 to the minus 5th, multiplied the top, divided by 1. And then if I do experiment 2, times what should I get this time? The same answer, right. K stands for constant. As in, we constantly get the same answer. And so, this reaction always has the same ratio. It always has the same ratio. So in truthfulness, the way I created experiment 3's data is I plugged in the equilibrium constant, and I left these two values at the top as x, and I said, you know what, I'm going to make the bottom 2 molar. So I created the data to fit this problem. So I cross-multiplied by 2, and I got 3.6 times 10 to the minus 5th is equal to x times x, also known as x squared. And then I took a square root. Yeah, I took a square root of both sides, and I got the 0.006. All right, so like I rigged the data so I knew it would work, because I used the constant, and I set the bottom value as 2, so I could create something that would work okay on the top. Does that make sense? That's what's nice about equilibrium constants. That's why they're useful. If you know the constant, you can use the constant. All right. Más preguntas aquí. Is that the last question? No. Not even close. How about we just stop anyway? I just want to take the test, really. All right. I guess we'll go over some more. More Le Chatelier stuff. SO2 is removed from the reaction vessel. Which way would this reaction shift if SO2 is removed? It would go to the left, yeah. If you remove the SO2, it's going to shift left to replace it. SO3 is added to the reaction vessel. We just mean the piston or the container. Yes, if we add SO3, it's going to shift to the left to get rid of what we just added. All right. And then oxygen is removed. It's going to shift to the left. In case you weren't paying attention, the answer was left, left, left. Right. Correct? Don't say right after that. All right, E. These questions here, we have heat, and heat. Increasing the temperature would shift this one to the right or left. That was a long pause and a very quiet pause with a few people go, stuff. So let's just kind of go through this again. So heat plus hydrochloric acid would go that way. If, however, the heat was removed, then the reaction can go that way. So you have to think of the heat almost like a physical object in the game. Now, if they're increasing the temperature, it's like they're adding heat. So by adding more heat, this reaction is going to shift to the left. The other two reactions would shift to the right because heat is a reactant. This is usually described using the enthalpy or the heat sign. So this is the heat of the reaction. And this one is losing energy, so it's negative. These other two, they're gaining energy, it's positive. When we were going over this in the notes and stuff, we compared like ice and water. Ice versus water. Which side would you add heat to force it go the other direction? Yeah, it's heat plus ice gives you water, right? If you add more heat, you're going to get more water. But if you subtract the heat, you cool it off, you're going to get more ice. This is a real nice, simple example to keep in your brain when you're doing these temperature reactions, all right? It's real easy to get confused and say, I'm adding the thing, and go the wrong way. It's a 50-50 shot. Actually, it's not a 50-50. There is a third very rare answer, which is neither or no change. It doesn't really occur with the temperature ones, but it can occur with some of the others. Let's go over number 18. which number 18 is actually the same reaction as number 16. I don't know if you noticed, it's SO2 and SO3 and stuff. Ooh, that's in my beard. Okay. Yeah, when the microphone hits your beard, I think it's scratchy. So, suppose the reaction is at equilibrium, blah, 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 indicate which way it'll shift. SO2 is added. That one would shift to the right. SO2 is a reactant. Adding more SO2 is going to shift to the right. SO3 is liquefied and removed. If SO3 is removed, it would shift to the right. So that's a good point. It says some is removed, but you got to remember, this thing is in balance. Any change they make is going to cause it to shift. If they remove a little bit of the SO3, it's not in balance. Go back to the marker flinging exercise. There's a point at which he had 6 and I had 2, and we were in balance. Well, if we remove 1 or 2 of his, we're no longer in balance, and then we need to get back. The vessel size is decreased. So it's going to go to the side with less moles. Which side has less moles? The right. This side has 3 moles. This side only has 2 moles, so it's going to go to the right. A catalyst is used. A catalyst gets you to equilibrium faster by changing the energy. But if you're already at equilibrium, yeah, it's too late. It's no change. No change. The triangle stands for change. That's me, technically. So, if the equilibrium constant is yada, yada, yada. Well, before we do that, let's set up the expression. This reaction doesn't say high once. It says high twice. So it's high squared over H2 and I2. It's been a long time since I yelled, but I want to remind you guys what that's right. What the guy in the back said, it's multiplication, not addition. So make sure when you set these up, those are multiplication on the top or the bottom. Now that we got the setup, we're going to plug the numbers in. Do we have a value for K this time? We do, yeah. 51.47. What else do we have values for? Concentration of HI is 0.5. And the concentration of hydrogen is 0.069er. And I don't know the iodine, so I'm going to put an X in there. And oops, I made a mistake. What'd I do? I forgot to square that number, didn't I? Now that I have this set up, I algebra for X. I manipulate the variables to get to X. I'm going to use my 3 things again. That means X would equal 0.5 squared over 0.069. Does the 51.47, does that end up on the top or the bottom? On the bottom, right? Because we have to divide it to the other side. And man, I had the X answer hiding somewhere. There it is. And so, the value for X is 0.070 molar. If I was not confident in my algebra skills, which I think I'm doing okay with my algebra now, what could I do with that answer to test myself? Yeah. I could plug that in and see if I get 51 point something, right? That's the one thing I liked about equilibrium questions when I was in your space, is that I could immediately test the answer. And then I would feel good or bad about it. And at least I would know I needed to go back and redo it. Let me pause for 2 seconds. All right. I think we hit everything. Do you all have any questions before we get started? You feel like you know everything? Good. Oh, thank you for the pass. Very excited. You just got recorded. This whole interchange just got recorded. Oh. Okay. Thank you. All right.